we're going to be talking about two topics today. Today, in some ways, represents the last day of divergence within this course. Divergence in terms of covering multiple modeling methods. We're going to be finishing up the third major dynamic modeling method that I talked about, which is discrete event modeling across the centric modeling. And I'm just going to be making some concluding remarks about its incorporation of visual representations in AnyLogic, just so you folks are familiar with the mechanisms that are in place under the surface there. Secondly, I'm going to be talking about the integration of dynamic modeling with another very, very important type of modeling, one that may be used as much, if not more, than any of the strategies we've been talking about dynamic modeling, and that is the use of decision trees. Decision trees to help reason through decisions in the context of uncertainty over time and consequences for particular outcomes. So it turns out that decision trees are an extremely popular way of trying to think through decisions, decisions which need to unfold in light of unfolding observations about what's going on in the world. And while it's little appreciated, this technique of decision analysis, the techniques of decision analysis can be combined very fruitfully with dynamic modeling. This is an area where our group has once again contributed, and it lends itself to a very powerful sort of synergy of modeling techniques, where the decision trees are used to understand policy space and reason about alternatives in a computationally frugal way, and the dynamic models are used to capture the dynamic complexities involved. So we're going to be taking a glimpse at that today. And following this, basically what we're going to have is a discussion of components of modeling processes which are pretty much in common with all of these techniques. So those include things like sensitivity analysis, calibration, a little bit of parameter estimation, model debugging, model output, data accumulation, that sort of stuff. Okay? So it's kind of going to be converging. Today is the last day of divergence. First, I want to talk about visual representations. This integration with the type of modeling we talked about last time of visual depictions of entities, resources, environments, etc. So the basic deal is, so you folks will remember from last time, when we have discrete event modeling, when we have this process-centric modeling, there are several key components. We have these entities, which are more or less passive, typically, flowing through a system. And we have a set of processes that operate on those entities as they flow through. But the operation of those processes is gated by, is constrained by the availability of resources. So a given process, let's suppose a procedure operated upon by a doctor, let's suppose checking into the hospital. Each of those is associated with resource needs. So the procedure, you might need a doctor, you might need an anesthesiologist as well as a surgeon, for example. You might need a team of nurses. You might need an operating theater. Perhaps there are certain types of endoscopes or what have you might also be required. In the case of checking into the hospital, you might need the triage nurse to be free so she can take down your name. And if those resources aren't free in this sort of modeling, what happens? What happens if in the midst of you're flowing through, an entity flowing through these processes, there's no resources available? They wait. Yeah. They queue up. So if they're waiting for that seizing of resources, as we called it, this association between them and a resource, this reservation of resource for them, this assignment of resource for them, we used a couple terms for it, but fundamentally it's them being assigned to a resource for a certain amount of time. If that resource is not available, they wait for it. They await it. there's no wonder that this sort of modeling is of quite some interest, incidentally, in terms of computational processes. You have queues associated with waiting for a server to handle them, for example. You have weight locks associated with access to databases and other resources. So within this context, we have these resources required to serve entities so that they can go through processes. And we have these flow maps whereby they move through it. So it turns out we focused last time on the logical flow, although we did note the availability of visual depictions, such as fighter jets for doctors. However, I wanted to just emphasize and, if not complete, at least flesh out some of those ideas. So fundamentally, in AnyLogic, when we're pursuing this sort of modeling, it is typically accompanied by a visual depiction. And I'm going to show you some of the simple aspects of that depiction here today. Bear in mind that some of the example models provided with AnyLogic exhibit much more sophistication in terms of their depiction of what's going on, using 3D views, for example. So here, entities will be associated with icons. Resources can be associated with icons and some home locations. Why aren't entities associated with a home location? Anyone? Why don't we have entities given a home? Yes, and they typically come in at a defined point, a source, and they disappear at a sink. And they're typically in the process only for a certain defined period of time. I should be careful about that. Maybe not defined period, a certain finite, bounded, if not bounded, at least finite period of time, certainly. One would hope it's finite. It's rare that they stick around for a persistent way. You can have loops. Entities could go back and kind of, they have to see the triage nurse again after being evaluated for one procedure so that they can go to another ward or something like that. But often it's a small number of times of iteration. So typically entities flow in, flow out, disappear when they flow out. Resources are the persistent things. Resources are the things that hang around, entity after entity, doing their job. Okay. And resource pools will be, the resources will lie in resource pools, and the resource pool will be associated with icons, sometimes one for busy, one for idle, for example. Further, though, we saw movement. We saw movement taking place over visual space. And this movement networks are associated with routing paths. And AnyLogic actually takes care of the routing. So if you say, I want to move to this certain node, it will figure out how to get you there on we looked into this last semester, and I think it was on a least distance type of basis. Okay. Here we'll often want to move a resource or icons, it's actually, or entities among different locations. So we'll tell the entity, hey, go to this procedure room, for example, or go to a location of a fixed resource. So in order to do this, AnyLogic is kind of a funny way of depicting this visually, although it's kind of true to its visual metaphor. So here we have this network. What is this network group? What was the function of a network here? We're not talking about scale-free, random, the Poisson random networks. We're not talking about small world. What sort of thing are we talking about in this context? Process modeling network. Yeah, exactly. And resources, as defined by resource pools. Here are 3 of them. Entities, and in fact, a set of visual depictions associated with them. How does one get into a particular network? Is this flow path associated with this network in some sort of static way, that it's one of the things we assign to this network? How do we get into this network? Yeah, exactly. It's really, I was going to scroll up here, but it's not. It doesn't lend itself to it. So actually, there's a network exit and network enter. And what that means is actually this flow path is not inherently, in a static sense, associated with one network. You could have a split, and one person goes to the maternity ward, another goes to the critical care unit, another goes to the emergency room, and those could all be captured. The semantics associated with those particular wards could be associated with the network enter, network exit, for example. So this network groups together resources, to be sure. It groups together some information about the sort of environment for this, the paths associated with that environment, in a way that's going to allow you to have sort of self-contained logic for each of the self-contained components for each of them. So in any case, we have these networks, and this network can be associated with paths that are defined, in fact, with visual information, define what's called network groups. So if you look over here, and I am remiss not to show it right now, it's under presentation, there'll be a thing which says network group. Okay. This groups together a bunch of resources that this network knows about. So here, for example, it knows there's a certain rectangle associated with a waiting hall. That's got that guy over there, the staff waiting room, which is somewhere up here. Proc room 1 and 2, and proc room 3 is down here further. So it knows about these resources, and hence it can interpret names as binding to these resources. That's sort of defines the scope of its knowledge of routing, for example. And you'll notice there are these paths here. Furthermore, there's actually kind of an odd shape here in these paths, and we'll get to that. One thing is, entities here they're created at the source. They'll leave at the exit. They come into being, like Athena from Zeus's head, springing into being, full blown. And they can come in a variety of ways. We noted they could come in with a RAID or inter-arrival time or manual. This will be valuable when we get to hybrid models between this and agent-based models, for example. But one issue is that we define the shape we want to use for them. Here we associate with a shape patient, okay? And actually, this shape patient, this does not have to be part of the network group. It's aware of that. I think it's really the routing that depends on the network group. Similarly, resources can be associated with idle and busy shapes, and they can be associated with a home node. Home node being drawn from this thing here, the staff node in this network group. Here, when we enter the network, we say, okay, what network do we want to enter? What's the entry node associated with it? And you'll notice that you associate a speed with this. And this is one of the reasons I argue that that the visual representation goes beyond even the importance of the visual representation goes beyond simply providing a convenient way to visualize what's going on. It actually is going to matter for logic in terms of how quickly things happen in the simulation. It's not merely epiphenomenal. It just depicts what's going on in some sort of way. The fact that we have a certain speed associated with agents is going to potentially cause queues to be shorter or longer, because it will take longer for someone to get over to a certain place, for example, and that may allow someone else to be finished by the time they're over there. Yes?
What does the speed actually determine? Does it determine the amount of time it takes them to reach from node A to B, or the speed at which they move along that path?
Yes, it's the speed at which they move along the path. So in AnyLogic, each of these squares, there's some big squares here and then the smaller squares. The smaller squares are, I think they're 10 by 10. And what this is saying is essentially for each logical time, each logical unit of time of the model, you move 10 pixels. So one of these smaller squares across. And so if you are heading as a patient, say, from this room here to the proc room, together with a doctor, carrying a scope. Remember, that's what happened. The Doctor and you both have a certain speed associated. The Doctor may be a fighter jet and, you know, have all the afterburners on and can move really, really fast. But if you as a patient are limited in your speed, maybe, for example, you're a handicapped patient, in which case you're in a wheelchair and you're limited to go 5 units, and maybe other patients can go 10. Depending on the vagaries of the situation, on the speed of the entity and the resource, it's going to take, you're going to go at the minimum of those speeds, and you have to go along this path here exactly. And that's going to just, that's going to be, your speed is going to dictate how you know, the rate of progress along this path. Okay? And it's going to be routing you via an appropriate shortest path to the appropriate destination that you said you want to go to. And it takes care of that logic for the routing. Does that make sense? Okay. Not a trivial matter, this whole issue of speed, routing, delays, because the people who use this sort of modeling, and I mentioned, for example, a nursing home that we work with, they're very interested in how does layout affect things. And, you know, if people are moving around this facility, if we place things closer to certain resources, will it speed things up appreciably? And the real question is, where are the bottlenecks? And maybe you speed this up, a certain process up, but maybe it's equivalent to, you know, making your driveway, you know, 5 lanes wide. I mean, that's not the real slowdown. That's not the bottleneck in getting you to class every day, your driveway. You could make it 100 lanes wide. You know, I used to drive on highways in Southern California, routinely 10 lanes each direction. And by the way, like a parking lot sometimes of the day. And you know, it turns out that sometimes it matters and sometimes it doesn't. Sometimes investing in things addresses the real bottlenecks and sometimes it doesn't. And the sort of bottlenecks you're investigating here often have to do with location of resources and queues that come about because of unavailability of resources. And so the speed issue is non-trivial. The speed issue matters for a lot of cases. And what's really nice about this is that the time it takes to undertake processes like moving someone from A to B is an emergent property of the situation. So in other words, it depends on this, on the underlying speed, and you could potentially have speed change based on congestion conditions or something like that, which gets interesting. And AnyLogic has this quite large pedestrian library, which is quite intriguing for, you know, simulating the flow of pedestrians into a subway tunnel and stuff like that. Recognizing that they need to avoid each other while walking, and therefore there's natural slowdowns. So here we have a movement network which is defined by polygons and rectangles. So what's going on here is we have these lines, which are nothing more than classic polylines from presentation, linking things up. And you'll notice that these kind of junctures, these nexi, shown here, which allow one path to link to another. The fact that these are joined allows someone coming up from that to go down, etc. And these polylines and rectangles that are used for routing are defined in this network group, which is associated with the network. Okay, and you can dictate whether you want things to be visible or not. Now, what adds further texture to this is that there are certain lines, like this red one in particular, which are used for different purposes. Specifically, this is not a routing. This is not a sort of cross-wall routing that allows a doctor as a fighter jet to burst through a wall to the next patient. This is instead a line which actually defines a set of resources. So with every crook of that line, with every bend of it, you are defining, in other words, every kind of vertex among line segments, you're defining a certain location. And it's basically delineating these 3 rectangles as being associated with a certain resource, namely this thing here. You notice this is in the Procrum resource, and it says the home is defined by the path across nodes, and the home path that is used to judge that is this one here, this sort of red line. this will implicitly dictate, although it's scrolled up here, this implicitly dictates the number of points on this line here, 3, 1, 2, 3, dictates the number of procedure rooms. Okay, so the fact that we have 3 of these says the 3 procedure rooms. That's implicitly defined by the line. It's an interesting graphical way of depicting it. It might not have been the one I would have come up with, but it does delineate, you know, the resources graphically, and it provides a way of doing so, you know, in a visual fashion that may be distinctive. So the rectangles touched by this are associated with one locations. Okay. You mean like that just sort of went off into this? I think it would ignore it because it's already in this. But if you were to go connect it to this guy up here, then it would view this as a procedure room. Now, what I can't speak about is, would it recognize there's a conflict because this is simultaneously the waiting hall and a procedure room? My guess is that it would treat it as a procedure room also, so they might start here, and then the doc would arrive with the scope. Let's go to the procedure room, and then they just stay there and conduct procedures in the waiting hall, which.
Shameful procedures conducted in front of 50 other people.
This is an ophthalmology model for a good reason. So there's no, there's nothing. But well, okay. So maybe people don't want, you know, things squirted in their eye, you know, while other people are around and so on. You can appreciate that. In any case, that I don't know what the exact semantics by which it would resolve this. It might complain, it might not.
But if you were building this up from scratch, you would first draw the root and then
Yeah, exactly. And if the line just went here, my guess is it would probably ignore it and say, oh, I don't know about that one, you know. But I can't be sure. It's fun to kind of perturb it and poke it and see how it reacts. Okay, so if we have certain nodes defined by, you know, as certain locations, like the exit location, we can then say in the network move to, remember there was network send to, network move to. What was the difference? Who can tell me? Network send to versus network move to. Yes. Excellent. So send to sends a resource from A to B, and often the destination may be implicit. So it's a resource associated with a certain entity, the entity that's flowing through here. And it's basically saying, send this sort of resource associated with that entity to this other place, which is often, say, a fixed resource associated with that same entity, or a portable but not inherently moving resource associated with the entity. We'll send it to that associated with the same entity. Move to, by contrast, moving the entity. And here it says move the entity to the exit, in which case it will move it to a specified node. Okay. So those are some visual sort of comments on this. Another thing to bear in mind is, with respect to this sort of modeling, it makes use by default of AnyLogic's built-in types for resource pool, entity. Generally, to customize this, if you want resources to record how long it's taken for them to undergo, or what fraction of the time they've been busy, for example, or entities to record how long it took them to go through certain steps. You can do so by subclassing those classes, and that's readily done. You would do so by creating a custom Java class that subclasses the appropriate class. And although I haven't concentrated on it, let's see if I have my do I have my AnyLogic up? No, I don't have my AnyLogic up. Let me fire up my AnyLogic. But fundamentally, there's a library which is which has at least passable documentation where you could examine the various classes and you can subclass them. In a lot of these mechanisms, do I have a slide on this? Yes. Oops, no. A lot of these mechanisms, it will actually ask you, okay, for example, this guy here, this source node. Let me see if I can go back and there we are. You'll notice that it says generic parameters entity here. This generic parameters refers to the class, which is in fact used to is associated with this source. So if you have some other entity class, like statistics entity, for example, you could just specify that there. This source would then be a source of statistics entities rather than entities. Now, of course, it would be a source of entities as well. That's why it says T extends entity. It's any type that's entity or subtype thereof. But having it explicitly as a statistics entity lets you directly from the entity involved, and it knows for sure it's a statistics entity. You don't have to cast it. You don't have to type coerce it to a statistics entity. Of course, here's the actual allocation of the entity as we talked about last time. So anyway, so with subclassing, generally speaking, you're going to subclass these things. Often you just add a method or two in some instance fields. So for example, you might have a network resource pool, and you subclass that, or you have an entity and subclass that. So here, for example, carrying around extra information, etc. We're going to see this featured in a model, probably not for another two or three lectures, where we have combination of hybrid modeling of discrete event and agent trace. Okay. We'll see them put together, and we will use subclassing to allow entities to keep track of their associated agent. And for example, send the agent messages saying the agent has been treated, or to inquire as to what particular resource, what particular doctor the agent saw last time they were in the hospital, that sort of thing. That would allow entities to be associated with persistent information that lasts outside of their strict life, which is otherwise delineated from here to here. Okay. So it gives them a sort of more persistent. Anyway, these are some comments on the visual sides of the discrete event modeling or process-centric modeling. Any questions on that before I go on to a final sort of more conceptually rich topic here? Questions? No? Okay.